What you're looking at here is a system diagram that shows why hydrogen vehicles require the entire mobility system to be built before the first consumer can really benefit, while electric vehicles scale in the opposite direction, as products that work before the system reaches completion. At the top, the title makes the core thesis explicit. Hydrogen vehicles require the system first, EVs do not. And underneath it, the subtitle makes the stakes clear. This is not a story about motors or batteries or fuel cells. It is a story about how infrastructure, cost, and utilization create two very different competitive futures for two technologies that appear similar from the outside. If we start on the left side of the diagram, you'll see the block labeled Hydrogen Vehicles. This block anchors the hydrogen mobility system. Just below it, the visual shows hydrogen fueling stations, complete with separate pumps, compression units, and signage, because hydrogen vehicles do not operate as isolated consumer products. They operate as endpoints of a larger and more complex chain. Right below that, the diagram places an equally important note. Electricity already exists. The point here is not to imply hydrogen does not use electricity. Rather, it is drawing attention to something that often gets missed in the hydrogen mobility debate. Hydrogen vehicles require hydrogen, and hydrogen must be produced. Electricity, on the other hand, already exists as a distributed infrastructure, ready to power EVs immediately. For hydrogen, the production layer becomes an additional upstream requirement that does not exist for electric vehicles. That additional requirement alone reshapes how quickly a technology can scale. If you follow the sequence from the left across the top of the diagram, the arrow above hydrogen says System, Vehicles, Demand, Utilization, Cost. That arrow is expressing the order in which components must align for hydrogen mobility to work. First, the system must exist. The hydrogen must be produced. The stations must be operating. The logistics must be ready. Only then can vehicles operate. And only after vehicles operate can demand emerge. And only after consistent demand emerges can utilization meet the thresholds necessary for the stations to be profitable. And only after that utilization occurs do costs begin to fall. Cost reductions do not drive hydrogen mobility. Utilization does. This is the opposite of what happened in EVs, where cost declines happened before perfection, not after it. Beneath the hydrogen production and station nodes, the diagram introduces the concept of a binary system. The idea is simple but powerful. Hydrogen mobility does not partially work. It either works or it does not. A hydrogen car without a hydrogen station is not a car. It is a stranded asset. The system must function as a complete whole to deliver user value. And once you require system perfection before user value, you create extremely high barriers to early adoption. Systems that require perfection before adoption scale slowly, if at all. Below the binary system label, the diagram lists three more attributes: high upfront capex, plus demand risk, utilization, must be high early, and shared risk, financing discomfort. And each of those attributes reflects a different layer of stress inside the hydrogen mobility system. The high upfront capex reflects the cost of building hydrogen stations and hydrogen production assets before demand exists. Demand risk reflects the uncertainty that vehicles will show up in sufficient numbers to make stations profitable. Utilization risk reflects the fact that hydrogen stations require high throughput early in their life to avoid becoming stranded assets. Financing discomfort reflects the perspective of lenders and investors who cannot finance stations profitably unless cash flows are predictable. The mobility sector is not like industrial hydrogen, which can contract with long-term off-takers. It is decentralized, consumer-facing, and unpredictable. Those structural differences matter. Now, if you move your eyes to the very center of the diagram, you'll notice a pipeline with a dollar symbol in the middle. This is a financial metaphor. It is connecting the hydrogen mobility chain on the left to the electric mobility chain on the right. The pipeline is not about hydrogen or electrons, it is about money and risk. And the key insight is that for hydrogen, money flows before adoption, while for EVs, adoption occurs before full system maturity. Upstream capital must be deployed for hydrogen mobility long before utilization is proven. That is what kills systems under stress. Systems without utilization cannot service debt. Systems that cannot service debt do not grow. On the right side of the pipeline, the EV side tells the inverse story, and you can see that immediately in the sequencing arrow. Instead of system vehicles, demand, utilization, cost, the EV side reads infrastructure, cost, grid. But more importantly, at the vehicle block, the diagram notes vehicles sold upfront. That is the first crucial difference. Electric vehicles are purchased upfront, not after infrastructure exists. They function immediately because the underlying energy system, electricity, already exists everywhere that matters. Drivers charge them at home, at work, and later at public stations. EVs do not require perfection to create value. They create value first and the system catches up later. Below that, the diagram adds, electricity already exists, reinforcing the point that EVs tap into a pre-existing infrastructure. That pre-existing layer removes the most difficult barrier to adoption for hydrogen mobility, having to build an energy infrastructure before consumers get value. Underneath that, the diagram introduces the idea of an incremental system. EV mobility scales incrementally because infrastructure can be deployed modularly. Home chargers, workplace chargers, and public chargers all fill different roles, and none of them need 100% utilization to be financially viable. Unlike hydrogen stations, chargers do not need to operate continuously at high throughput to break even. They are low capex, modular, and flexible. If a charger sits underutilized for a time, it does not collapse the system. It merely delays its own payback. That is what the bottom right green box in the diagram means when it says low capex plus distributed. Distributed systems absorb stress. Centralized systems amplify stress. Beneath that, the EV side of the diagram lists utilization, low, financing comfort, positive learning loop. This is the feedback mechanism that EVs enjoy. EVs start at low utilization because the utilization is private and distributed. Every driver becomes their own micro-utility. Financing comfort emerges because lenders and investors see predictable cash flows. Public charging scales not because it is needed to make EVs work, but because it makes EVs more convenient. That distinction matters enormously. Convenience-based infrastructure scales differently from necessity-based infrastructure. Convenience-based infrastructure can operate at low utilization early. Necessity-based infrastructure cannot. If you now drop your eyes to the bottom band of the diagram, you see the synthesis. On the hydrogen side, it reads, hydrogen mobility collapses as a system under stress, followed by the line, perfection required before adoption. That phrase summarizes the entire failure mode. Hydrogen vehicles must wait for the system to be complete before consumers adopt them, and systems that must wait for perfection are fragile. On the EV side, the bottom band reads, EV mobility survives stress and scales as a product, followed by the line, adoption creates a path to perfection. The order of operations is reversed. Perfection does not precede adoption. Adoption precedes perfection. And at the very bottom, below the synthesis band, the diagram gives the final thesis sentence. EVs scale as products. Hydrogen vehicles must scale as systems. And beneath that, in even smaller type, the conceptual foundation. Systems that must work before adoption collapse. Systems that work before perfection scale. It could not be expressed more clearly. The fate of these two technologies diverges not because one is more efficient than the other, or because one has better engineering, or because one has better marketing. Their fate diverges because one aligns with how systems scale, and the other does not. This is the point in the video where we introduce the H2 hub, and it fits naturally because diagrams like this are not about hype. They are about execution. Hydrogen's future depends on execution. It depends on offtake agreements, permitting, incentives, infrastructure, and final investment decision. That's why we built H2 Hub, to train the next generation of hydrogen developers, consultants, and investors who will navigate this phase of the transition. Hydrogen is not a consumer technology, it is a system technology. And system technologies require system understanding. If you want to go beyond headlines and understand how hydrogen actually reaches bankability, commissioning, and operation, H2 Hub is built for exactly that purpose. Returning to the diagram for closing synthesis, the message for the viewer is not that hydrogen vehicles failed because hydrogen is bad. It is that hydrogen vehicles failed because they entered the wrong part of the mobility market. Hydrogen is a system-first energy carrier. It shines in roles where utilization is guaranteed, where refueling is centralized, where logistics are predictable, and where infrastructure can be justified before vehicles arrive. That describes aviation, shipping, ports, rail, steel, ammonia, and long-haul trucking far more than it describes suburban consumer vehicles. Electric vehicles entered the right part of the mobility market. They entered consumer vehicles first, where home charging provided a fallback mode and where adoption could begin before perfection. Once adoption began, cost declined. Once cost declined, scale accelerated. Once scale accelerated, infrastructure matured. Systems that scale do not begin as systems, they begin as products. And products that work before systems exist create the systems that sustain them later. For professionals working in clean energy, we include links to financial models and feasibility templates for hydrogen, solar, ammonia, and other project finance assets. These are the tools that developers, consultants, and investors use to evaluate real projects. Not in theory, but in practice. The energy transition is not about picking winners. It is about understanding how systems behave under stress. Technologies that survive stress scale. Technologies that require perfection wait for the future instead of creating it. That is the story the diagram tells, and that is the lesson hydrogen and EVs teach us as we build the next chapter of the energy transition.